Good morning everyone. Now we are going to discuss about potentiometric titrations. In the previous videos we have discussed about conductometric titrations. Volumetric titrations, generally we use an indicator to calculate to note the endpoint, but in potentiometric titrations we are going to measure potential difference. By measuring potential difference, we can calculate the concentration, or we can calculate the endpoint. We can determine the endpoint. And how we are going to do this experiment? Whatever the solution we are going to calculate is taken in a beaker. In this beaker, we are going to dip 2 electrodes, and these 2 electrodes are connected to potentiometer, which measures the potential. This is potentiometer. Which is going to measure the potential. These 2 electrodes are connected to potentiometer, and the solution, one other solution is taken in burette. Here we are taken 2 electrodes. One is standard electrode. One will access standard electrode, and the other will access reference electrode or working electrode. What are potentiometric titrations? If we calculate the endpoint or concentration of the solution by measuring the potential, we call it as potentiometric titration. In potentiometric titrations, generally we have 2 electrodes, and these 2 electrodes are connected to potentiometer to measure the potential difference. In the 2 electrodes, among these 2 electrodes, one will access standard electrode, and the other will access working electrode. Again, in potentiometric titrations, we have different type of titrations: acid-base titrations, redox titrations, precipitation titrations. Now we are going to discuss redox titrations. What is redox titration? In this titration, one will undergo reduction and the other will undergo oxidation. Both reduction and oxidation occur during this titration. If we consider one example, ferrous to ferric using chromate ion, dichromate. Here iron solution is taken in the beaker, and potassium dichromate is taken in the burette. With the addition of potassium dichromate to ferrous solution, this ferrous ion will converted into ferric ion. So there will be change in the potential with the addition of potassium dichromate to iron solution. So we are going to measure the potential, and after measuring the potential, if we plot a graph between volume of potassium dichromate versus whatever the EMF we measured, initially the potential rises slowly, and at the neutralization of iron, the potential increases rapidly, and after neutralization it will be increasing slowly. And how we are going to calculate the endpoint here? Again, we have to do fine titration. First, with the addition of 1 ml of potassium dichromate to iron solution, we are going to plot a graph between volume of potassium dichromate versus EMF, we get a rapid increase at endpoint. So to calculate that endpoint, again we are going to do fine titration between these two values, between these two volumes. If it is 6 and 7, now again we are going to do the same setup. Again, instead of this 1 ml, we are going to add 0.1 ml. This is for rough titration and this is fine titration. Again, up to 6 ml, we are going to add potassium dichromate fastly, and after 6 ml, then 0.1 ml is added. Then again we are going to measure the potential displayed in the potentiometer. Next, after doing that fine titration, again we are going to plot graph between volume of potassium dichromate versus change in the potential to change in the volume. After doing fine titration, we are going to plot a graph between volume of potassium dichromate versus change in the potential to change in volume. Then we'll get a graph like this. Where the highest peak is obtained, it gives the endpoint. Like this, we are going to calculate the endpoint using potentiometric titrations without any indicator, just simply by using the potential. Then coming to the applications, what are the advantages over the volumetric titrations? If the solution is colored, we cannot perform the volumetric titration because we are going to calculate using endpoint with color changes. But without adding indicator, if even the solution is colored, we can calculate the endpoint or we can calculate the concentration simply by using potentiometric titration. If the solution is turbid, like if the solution is not clear, we can even calculate that turbid solution concentration also using potentiometric titration. And if the concentration of the solution is very dilute, for example, if concentration is 0.0001, we cannot perform the volumetric titration. In that case, by using this potentiometric titration, we can simply calculate the concentration even if it is dilute. Thank you.